All right, let's get to lecture 23, which is chapter 9, particularly section 9.3 on diesel cycles. So we'll simply go through a thermodynamic analysis of diesels. So what is a diesel cycle, which is a very old cycle here? It looks like the Otto cycles, like the gasoline engine. So you have the piston. The first stage is input air, and then you compress the air. So initially the inlet valve opens, lets air in. Then in stage 1 to 2, you have an isentropic compression of the air from the bottom dead center to top dead center, just like we had in the gas engine. Note that there is no fuel in the air during this compression stage. Once the piston is at the top, you have a stage 2 to 3 of injection of the fuel. So there is a fuel injector in here that injects the fuel. The pressure and the temperature here are so high that as soon as the fuel comes in, it catches fire. The combustion takes place at the moment it's ignited and at constant pressure. So what happens then, initially, is that the fuel is injected for a certain amount of time during the downstroke. And we will assume that the combustion takes place at a constant pressure while the piston is coming down. So the combustion is quite slow. Then somewhere halfway in the downstroke, the fuel injection is ended, and the hot gases that come from the combustion process continue to push the piston all the way down. So that is stage 3 to 4, which is a classic isentropic expansion. So note that in 2 to 3, you have two things that happen simultaneously. One is the combustion, so the addition of heat, and the second is the motion of the piston, therefore changing volume, therefore work. 2 to 3, you have both work and heat. 3 to 4, you no longer have heat, the combustion is finished, but you continue doing some work. And then 4 to 1 is the same as with the gasoline engine. The exhaust valve opens, and you have the exhaust stroke where you push the gas out. So the major differences with Otto is that the heat addition occurs relatively slowly during a constant pressure process starting at TDC and extending for a fraction of the time down. That fraction is a cutoff ratio, R sub C. It measures the volume when the ignition ends and when step 3 begins. So the fraction of the volume between the moment you're at top dead center and when the ignition ends, that's R sub C. You, of course, have the old R that we had also in the gasoline engine, which is a classic compression ratio, the volume ratio between when the piston is at bottom dead center and at top dead center. All right, that's a diesel. Now we are going to make an air standard diesel analysis, diesel cycle analysis. So we have 1 to 2 isentropic compression, classic isentropic compressions here. 2 to 3, this famous new constant pressure heat transfer, constant pressure combustion from 2 to 3. So in a PV diagram, this is a horizontal from top dead center to some way down in the volume change. Well, this way down in volume change is R sub C. That's the cutoff ratio. It's the ratio of V3 to V2. It's the cutoff ratio. Whereas, of course, we have the classic compression ratio, which is the ratio of V1 to V2, is here. Okay, so now the fuel stops being injected and we go down this path, which is the isentropic expansion. It's the power stroke. So the power stroke actually happens to have and this and that, but this is the classic part of the power stroke like in an Otto cycle. 4 to 1, constant heat volume process in which the heat is rejected. That's just like an Otto process here. So note now that you have these relations between the volumes of the cylinders. V4 over V3 is R over R sub C, because it's V4 over V3, V2, V2, and that is V4 over V2, and this is V2 over V3. Let's now move to the air standard analysis and the equations for compression, for work, and for heat. So the first part is the classic compression work between 1 and 2. which is the same as we had in the Otto cycle. So W12 over mass is U2 minus U1. That's simple. The other one that looks just like what we had in the Otto cycle is the work done after the combustion stop between 2 and 3. That's also an isentropic power stroke, isentropic expansion. It's U2 minus U3. And the third one that's similar to the Otto is 4 to 1, which is when the exhaust valve opens. So the heat out then becomes simply U4 minus U1. Nothing new here. The new part is here. So when we now look at the work in 2 to 3, 2 to 3, you have both work and heat because the piston moves, yet you have fuel that keeps being injected. So the work is the motion of the piston. W23 over m is the integral of p dv. We assume p is constant. That's just to make the integral simple. So that's p2 v3 minus v2. Very good. Now the internal energy change between 2 and 3, U3 minus U2, is both the heat and the work. This is simply an expression of the first law of thermodynamics. And both exist. Neither of these two is zero. But this one, you know, because you calculate it as the ratio, pressure times differences in volumes. Specific volumes because we divide by mass. So we rearrange this Q23, it's U3 minus U2 plus W23. The W23 we like that. And we have Q23 over M is U3 plus, well, U3 minus U2 plus P2 V3 minus V2. So this really is P3 equals P2. So U3 plus P3 times V3, that's H3. U2 plus P2 times V2, that's H2. So you have now here, surprise, surprise, enthalpies that appear instead of internal energies. So even though the system is a closed system, and we did this system analysis, Q23 is a delta H and not a delta U. And the reason is because this work and this heat addition occurred at the same time. Don't forget these two ratios, they will come back. So now let's put the whole thing together and calculate net work and efficiency. So work really has three terms. Work has, on the one hand, the classic expansion in the power stroke, 3 to 4, U3 minus U4. You have, of course, the classic compression work that you have to input in your system, U2 minus U1. And you have the work that's being done during this heating part of the stroke, W23, which is PV3 minus V2. Now, because of this, of course, the heat that goes in here, Q23 is H3 minus H2. We have just seen that. Whereas the heat that you have lost here, Q41, the cold side out heat is U4 minus U1. So now the total work of the cycle is the two parts of the work in classic isentropic expansion, the work during the heating minus the work during the isentropic compression. And that is the net work, which has to be equal to the heat in minus the heat out. The efficiency is the net work, which is 1 minus Q out over Q in, which you can express as U4, U1, and here is enthalpies, H3 and H2. So that is an equation you actually have to more or less remember that it exists. It's a special thing, special case for diesels. Now, from here on, you have to do exactly like we did with the Ottos. You have to use a way to get from the points 1 to 2 or 3 to 4 using the isentropic transformations. So now we do the same thing as we did before. In air standard analysis, you use these reference volumes, which are really the same thing as entropies, and you have VR2 is VR1 over R. So you need this to derive the thermodynamic properties of state 2 from those of state 1. That equation hasn't changed. Now, the equation that has changed for the diesel is the expansion from 3 to 4, which is an isentropic expansion. In the case where we had the Otto cycle, we had 3 to 4 times R, the compression ratio. And here, if you apply exactly the same equations that we had, but for the diesel, you see that T3 becomes the RC times T2 and not the R times T2 like you did in the Otto cycle. Now, to get entropy 4, or reference volume 4, that is the same as we had for the Otto cycle. So V4 is given as V reference 4 is given as V reference 3. That's V4 over V3. But because of the properties of the ratios of the diesels, it's not just R times V3, like in an Otto, but it's R over RC times V3. So these things you have in your book. When you will have exercises to solve, you'll have to look whether you're Otto or diesel, and these formulas are different for Ottos and diesels. If you do your cold air standard analysis, so this is the analysis where CP and CV are temperature independent, and you can do everything with the CP to CV ratio K, and then you get these formulas for the cold air standard. T2 over T1 is R to K minus 1, which is exactly the same thing as for Otto, because this isentropic compression is the same. But 3 to 4, T3 to T4, is not just R2 powers 1 over R2 power K minus 1, it's RC over R2 power K minus 1. And you're ready to solve all problems with diesels. One last thing, applying this cold air standard analysis to derive the thermal efficiency, which is 1 minus U4 minus U1 over H3 minus H2, you notice that you have in cold air standard analysis, U4 minus U1 is CV, T4 minus T1, whereas H3 minus H2 is CP, T3 minus T2. So here appears the famous ratio of CP over CV, K. You have efficiency is 1 minus 1 over K times this, IK minus 1, IK minus 1, and IC minus 1. So you notice now that if you have a diesel cycle, K shows up here, and you have both the compression ratio and the cutoff ratio that shows up in the efficiency. So here is this efficiency as a function of compression ratio. If IC is 1, you simply end up with an Otto cycle. So careful, these you don't divide by 0 here. This is undetermined, you have to go back. So here is your Otto cycle. And if you apply diesel cycle with RC's cutoff ratios in the middle of the power stroke, RC is 2, you have a decrease in efficiency, and RC is 3, you have a decrease in efficiency. So what is all this story about automotive manufacturers in Europe that say that diesel cycles are more efficient than Otto cycles and gasoline engines? Diesels have better fuel economy than gas engines, whereas this tells you the opposite. Well, the simple reason is that you can get diesels to work at much higher compression ratios, at much higher pressures, and at much higher temperatures than equivalent Ottos. If you were to try to reach the same compression with an Otto cycle as with a diesel cycle, your gasoline would simply explode before you get to top dead center. You can't do that. You have to have lower compression ratios. So whereas R for a diesel is maybe 20 or 22, R for a gasoline is 10. And so that means that you're derated. You have to compare the Otto cycle here to the diesel cycle out here. The diesel cycle wins, but just because it wins. It runs hotter, and it has a higher Carnot efficiency. And it can run hotter because auto-ignition is avoided by the fact that you inject the fuel at top dead center instead of compressing the fuel with a compression stroke, which of course leads one to concepts of why don't we make a hybrid where we can use the benefit of the Otto cycle as far as RC goes, cutoff ratio, so we try to keep the ignition as short as possible at top dead center, but yet we do an ignition where we inject fuel at the top dead center. We don't just compress the fuel during the whole compression stroke. And these engines do exist, hybrids between diesels and Ottos, and they are made possible because you have diesel injector technology, but yet a gasoline type cycle. So actually, the whole key to making diesel engines possible are these injectors, and I have a little off-the-cuff introduction here to diesel injectors. Basically, the injection system is the heart of the diesel engine, and it's also extremely expensive. It's the reason diesels are more expensive than gas. But there's another reason, is that the engine itself has to be made stronger because pressures are higher and temperatures are higher, so the forces on the parts are higher. But the most expense comes really from these injectors. The injectors have a long, long history. In the 200 years ago or something, when diesels were invented, Diesel himself used a fairly crazy air blast system. And then for the longest time, we have had distributor pumps that made direct injection. So what you had here is a high-pressure pump that was attached to the crankshaft, driven by the crankshaft. And that then had 4 compressors, each of which would inject the high-pressure fuel into the cylinders at the right time. So the pump and the timing system were the same. There's some strange things here. But today, all diesels use, well, not all diesels, many diesels use common rail systems where there is one high-pressure pump, now a very high-pressure pump, here, that takes fuel from the tank and that creates a rail that is a reservoir of high-pressure fuel, and that the injectors are actually switches that let the high-pressure fuel go from the rail into the pistons, and it's actuated by the engine control unit, electronic control unit here. Instead of the old system, the distributor system, where the high-pressure fuel pump would go to each cylinder in time, and the timing would be done by the fuel pump. This is a more efficient system. It's also more expensive. I have one last and quick view here on something that's called a Stirling engine. It's described in the book. We will not go over the Stirling cycle. It is entirely a hot air engine or hot gas engine. It can be run on helium gas. The combustion now is external, so it's not actually belongs in Chapter 9. It's not an internal combustion engine. You have an external source of heat that expands here, and this expanding air is sent then into an external source of cold. So you have the hot reservoir and the cold reservoir at the same time, a hot piston and a cold piston, and the motion is coordinated between the two. This is a very, very old engine, one of the oldest engines there was. It's also rather enormous. In other words, it lacks specific power. You have a very small load of gas to move a large machine. Now, it still is used in some very limited applications, cryogenic cooling applications, where it is based on helium gas. The cycle, I won't go into details in the cycle. You can look that up for yourselves. Thank you.